In this video, we're going to talk about the conic section, the ellipse. And now, geometrically, the ellipse is formed by the intersection of a plane and the three-dimensional cone, where the plane actually slices all the way through the edge of the cone, and it's not parallel to one of the openings. And so what it forms is an ellipse where the intersection lies. Now, an ellipse has a reflective property, where an ellipse has two foci, and we'll define an ellipse here in just a minute. But a reflective property of an ellipse is that if I have something that starts at one focus, and let's say a ray, it starts at one focus and it shines through that focus and hits the edge of the ellipse, it will reflect back through the second focus. And in terms of an application purpose in medicine, and I have an example right here, if I have a patient, let's say that has kidney stones, and the patient is located here at one focus, and we have a machine that emits some kind of wave, and what happens is that the machine that emits the wave, it can, if the person's inside of like an elliptical bowl of some nature, and no matter where that wave goes, if it's shot from its source, it will hit the edge and then go right through the location that we're trying to, I guess the location of the kidney stone, to help break it apart. And so what we're going to do is we're going to define the ellipse as the set of all points whose distances from two fixed points, which are called the foci, will have a constant sum. So the set of all points whose distances from the two foci will have a constant sum. Now, an ellipse has two axes of symmetry. It has a major axis, whose endpoints are the vertices, and a minor axis where the endpoints are called co-vertices, and the intersection of the two axes are called the center of the ellipse, which will take us to our equation of an ellipse written in standard form as x minus h squared over a squared plus y minus k squared over b squared is equal to 1. The only difference in terms of the orientation is the sizes of the denominator. Now, if an ellipse is elongated along the horizontal, x will have the bigger denominator. If it's elongated about the vertical, y will have the bigger denominator. Now, we have some terminology to talk about here. So the center is still h comma k in both cases. The major axis that has endpoints of that are vertices, the semi-major axis is the distance from the center to one of those vertices, which is always going to be a. It's either going to be a along the horizontal or a along the vertical. The distance of the semi-major axis, which is the distance from the center to a co-vertex, is represented by b. Now, there's a Pythagorean relation. So let's look at one of these pictures here, and we zoom in. So I have my center, I have my vertex, and a co-vertex. There's a Pythagorean relation that exists, where if I compare the distance from the center to a co-vertex and the center to a focus, which the distance from the center to the focus we're going to represent as being the constant c. We have a Pythagorean relation where the hypotenuse, if I see this right triangle, have a hypotenuse of a, which is, so the distance from the center to the focus, or excuse me, the distance from the co-vertex to the focus is the same as the distance from the center to the vertex. And I can set up a Pythagorean relation where a squared is equal to b squared plus c squared. And that's going to be very important for us because it's going to help us solve for a missing constant and determine how far away a focus is from the center. Distance from the focus to the center is going to be represented by c. Now, there's two axes of symmetry. We have a horizontal axis and a vertical axis for the orientations that we have through the ellipse. The focal axis is going to be the axis that connects the two foci together. And so that's one axis of symmetry. And then the other one would be an axis of symmetry that passes through the co-vertices. You don't really hear that one asked too much. Now, the eccentricity, that's a terminology. Eccentricity is a ratio formed by the distance between the center and the focus C to the distance from the center to the vertex A. So eccentricity is C divided by A, and the eccentricity of an ellipse is always going to be between 0 and 1. All right, so now we're going to look at a couple examples where we want to graph and find all the key features of an ellipse. I'm not going to talk about the directrix lines for the ellipse. That's something we would need to talk a little bit about if we were going to do some polar representations of conic sections, which we're not going to do for right now. So basically, I want to fill out this list so that way I can get a sketch. Well, looking at the ellipsis given, it's given to me in standard form. I want to first identify its orientation. Well, the orientation, since y has the bigger denominator, the orientation is going to be vertical. So what that means is it's going to be stretched like this. It's going to be elongated up and down. The center, h minus k, would be at -2, 1. Now we want to identify our constants. Well, a is going to be the square root of the bigger denominator for the ellipse. So a is going to be 5. B is going to be the square root of the smaller denominator of those terms. So b in this case would be 3. Now the Pythagorean relation, a squared is equal to b squared plus c squared. We would use that to solve for c. So we'd have 5 squared is equal to 3 squared plus c squared. And we're going to wind up getting c to equal 4. So now that we know our constants, we can find our vertices, co-vertices, and our foci. If we're elongated vertically, our vertices are going to be plus or minus a in the direction that we're elongated. So if we're elongated vertically, I'm going to add and subtract a from my center to get the endpoints of, or to get the location of each vertex. So plus or minus 5. So I'd have one vertex at -4, one vertex at 6. My co-vertices would be in the opposite direction. So my center, which lies here in the middle, my co-vertices are going to be to the right and the left of that center. So I'm going to add and subtract b, in this case, to the x value. So we have one co-vertex at -5 by 1, and one co-vertex at 1, 1. And now the foci are in the same direction as the vertices are from the center. So we have vertices that are up and down. Your foci are going to be in the same direction, just not quite as far. They lie inside of the ellipse. So we'd add and subtract c in the same direction that we're elongated at. So my foci will both have x values, in this case at -2. My y values, I take the y value of my center, add and subtract c. So 1 minus 4 gives me a y value of -3. And then 1 plus 4 gives me a y value of 5. Now our eccentricity, the elongation factor of our ellipse, is c divided by a. So we'd have 4 divided by 5. And that's the ratio of the distance from the center to a focus compared to the center to an ellipse. Or excuse me, the ratio of the distance from the center to a focus to that which is the distance from the center to a vertex. The closer the eccentricity gets to 0, the more this ellipse will resemble a perfect circle. All right, so over here we're going to make a scale for what we have. And so we have our center. I'm just going to mark the center, put an X there, because technically the ellipse doesn't pass through the center. We have at -2, 1. We have vertices at -2, 6. And so I'm going to put V's there. And -2, -4. We have foci at -2, 5. So they're kind of close together. I'm going to put a little F. And at -2, -3. And then we have co-vertices at -5, 1. So I'm just going to say CV. And at 1, 1. There. Now, something we can do to help us sketch an ellipse is to make what's called a central rectangle. We're going to make a rectangle that passes through the co-vertices, that's parallel to the focal axis. So it's parallel to the line that connects the two foci together. And then we're going to make the other edge of the box that passes through the vertices, that is parallel to the conjugate, or not, excuse me, the minor axis, where we have, this is our minor axis, and then our major axis would connect the vertex to the center. Now, to sketch our ellipse, what we would do is your ellipse is going to be tangent to the box at those vertices. So I would be tangent to my box at those vertices. I'm going to do the best that I can to sketch there. And so we get our ellipse there. So the ellipse is going to be inside of our rectangle, tangent to the sides of the box at those 4 points. All right, looking here at this next one. All right, so looking at this problem, we're going to identify the center. It should be x minus h and y minus k. So our center here is at -2, -3. The orientation, well, x has the bigger denominator. So that means if x has the bigger denominator, it's going to be oriented horizontally. And if it's stretched along the horizontal, what that means our vertices are going to lie to the left and the right from the center. So we have our center, and then we have one vertex on either side, and our co-vertices would lie above and below the center. Now to find the co-vertices and the vertex and the two foci, we would need to figure out our constants a, b, and c. Well, a is the square root of the bigger denominator, so in this case a is 5. And b is going to be the square root of the smaller denominator, which in this case is 4. And the Pythagorean relation, a squared equals b squared plus c squared, means that c is going to equal 3. And so we would go ahead and find our vertices. So the vertices are going to be located to the left and the right of the center. So that means my vertices are both going to have the y value of -3. The x value, I'd go -2 minus 5 gives me -7, and the y value -2 plus 5 gives me 3. I'd have my co-vertices would lie above and below the center, so their x values are still both going to be -2. I do -3 minus 4, which takes me to -7, -3 plus 4, which gives me a value of 1. My foci are going to be in the same direction as your vertices, so they'd be to the left and the right of the center as well. So I'd add and subtract c to the x value of my center, so my foci are both going to have y values of -3. I would add and subtract 3, so we have one foci, one focus at -5, -3, and then I have another focus at 1, -3. The eccentricity, the elongation factor of this ellipse, c divided by a, 3/5. Now the closer that number is to 0, the more circular it gets. The closer it gets to 1, the more stretched out and elongated it's going to be. All right, so we'll try to graph this. We have our center at -2, -3. I'm just going to mark that with an X. We have vertices at -7, -3. I'll put a dot there with a V. Now, remember the endpoints of the that are vertices are the endpoints of the major axis, which the distance from end to end of my major axis will be 2 times A. The endpoints of my minor axis are my co-vertices, which happens in this case at -2, 1 and at -2, -7, which means that the minor axis has a length of 2 times B. Our foci are occurring at -5, -3, so they're just slightly closer to the center than the previous problem. And then we want to sketch, so we're going to make this central rectangle. So the central rectangle that goes through the vertices, we're making our box. So it'd be parallel to the major and minor axes that goes through our vertices, and our ellipse is going to be tangent to the box at our vertices. So it would look something like that there. All right, let's look here at this next one. So I'm given the equation x minus 3 squared plus y plus 1 squared is equal to 4. And now this doesn't look like the standard form of an ellipse because the ellipse is set equal to 1 and I have denominators here. So what you could do is you could divide by 4 and make that, but I'm going to have the same denominator in both cases. I would hope that if you look at this formula, it looks like x minus h squared plus y minus k squared is equal to r squared, which is a circle. It's a circle that has a center at h comma k, and then our radius we would identify from there. So this is simply a circle that has a center at 3 comma -1, and the radius in this case is equal to 2, and so we would go graph that. And so technically we don't have vertices for this, but if we want it, a circle is equidistant. All points are equidistant from the center. If you wanted to make a box to contain your circle, you could. And then I would need to make myself be tangent to this box the best I could, where my circle would fit in. That's a terrible looking circle, but it would basically be the same way as the ellipse. but every point here, if I would have drawn it, the scale might have fit a little better, would be tangent to that box.